Welcome to the third lecture of week 3, and in this lecture we will discuss liquid fluidization. So, if you see this image, in the first image the particles are away from each other, it means particles are already at fluidized condition. So, this condition occurs when liquid velocity is equal to the minimum fluidizing velocity. Why I am telling this that liquid velocity? Because here we are discussing liquid fluidization. So, fluid we are considering as liquid. So, this is the condition when minimum fluidization achieved. Now, if you see second image, here particles are separated far from each other, they are more away than these are in figure 1, and this is achieved when liquid velocity will be much higher than that of minimum fluidizing velocity. So, liquid velocity is much higher than minimum fluidizing velocity. So, you see here, even if velocity are much greater than minimum fluidizing velocity, particles are spread almost uniform in the bed. Particles are spread almost uniform in the column. So, this is the effect of liquid fluidization. Through liquid, bubbles are not formed in the bed, and therefore, in this case particulate fluidization occur, not aggregative fluidization. So, when we are considering liquid fluidized system, these are generally characterized by regular expansion of bed that takes place as the velocity increases from minimum fluidization velocity to terminal falling velocity of the particles. So, you see here, when we are discussing liquid fluidization, the expansion of bed is regular. It is not like that in some section of the bed more particles are available and some are in some places no particle is available. The particles are spread thoroughly, the particles are spread uniformly in the bed, and that is due to liquid fluidization. And this happens when the velocity of the fluid is greater than minimum fluidizing velocity and lesser than terminal falling velocity. Now, what happens beyond terminal falling velocity? Because beyond terminal falling velocity, the particle will be carried away by the liquid, because when we are considering terminal falling velocity of the particle, it means particle falls with a uniform velocity. Now, the fluid velocity is greater than terminal falling velocity, the fluid takes the particle with it and it can be carried away. So, that is the condition when we have that condition we should obtain when we have to transport the solid from liquid. Now, in this case, as bed is regularly expanded. Now, in this case, when bed is regularly expanded, it means particles which are available that are spread uniformly. So, voidage we can calculate inside the bed, because almost uniform voidage will be uniform space for voidage will be appear everywhere. So, that can be related with the velocity. So, Richardson and Zucchi 1954 showed that for fluidization of uniform particles, UC by UI is equal to e raised power n. So, UC is basically the operating velocity at which fluidization occur. UI is the velocity at infinite condition, and how we will calculate UI, that we will discuss, and this should be equal to voidage power n. So, n is the index over here. UC is empty tube fluidization velocity or the actual velocity of fluid, and how we can calculate UI? UI expression is this: log UI equal to log U naught minus d by dt. So, you see here U naught we are considering with the free falling velocity of the particle. So, here indirectly we are relating actual velocity of the particle and terminal falling velocity of the particle with the voidage. Now, values of index n, which we have seen in the last equation, ranges from 2.4 to 4.8 for fluidization at a given value of Galileo number, and that can be calculated from this equation. 4.8 minus n by n minus 2.4, and which is related with Galileo number by this expression, where d is basically particle diameter and dt is the diameter of the column or tube. So, considering this expression, we can calculate value of n. Now, further, Khan and Richardson 1989, they have proposed a relation between ui and u naught. Ui we have seen, for ui we have already seen one expression in the last slide. This is another and more recent expression. This is ui by u naught equal to 1 minus 1.15 d by dt power 0.6. So, u naught is basically terminal falling velocity of the particle, and from here we can calculate ui. So, once we calculate the value of ui and velocity inside the fluid, inside the fluidized bed is known, so we can calculate voidage. But before that, we have to calculate index n by equation which we have just discussed. Now, another approach for computing index n is this, where n is equal to a naught plus b naught d by dt Reynolds number t power m. Now, what is this Reynolds number t power n? It is basically dt u naught rho by mu, where rho and d are the property of fluid. U naught is terminal falling velocity. So, you see Reynolds number t is nothing but the Reynolds number at terminal falling velocity. Now, when we are considering d by dt over here, d is for particle and dt is for column or tube. So, this can be considered when we have to consider the effect of wall. How we consider the effect of wall? Because this expression is almost negligible when we are considering dt value should be very high. What is the meaning of this? That if column diameter is very high in comparison to particle diameter, it means the effect of wall will not be then the movement of particle will not be affected by effect of wall. Then the movement of particle will not be affected by the wall of column. But this will be considered when diameter of tube is not very large in comparison to diameter of the particle. So, through this equation we can calculate n. Now, here we have again a few factors like a naught, b naught and m, and that we can calculate for different Reynolds number range. We can calculate these coefficients value. We can see the value of these coefficients for different Reynolds number from this table. Therefore, this correlation has been proposed for bed of spherical particle. However, with allowable error, same may be used for non-spherical particles while replacing d with the volumetric diameter of particle. So, you see using this expression we can calculate value of n for spherical particle as well as non-spherical particle, but for non-spherical particle instead of diameter we have to consider volumetric diameter of the particle. And you understand how we define volumetric diameter is the diameter of a sphere having same volume as that of the particle. And here we will discuss a few examples to illustrate how the governing equation which we have developed, which we have derived, how these equation will be useful for fluidization process. How we compute different parameter, how we compute minimum fluidizing velocity, mass flow rate, etc. So, to illustrate that, let us start with example 1. And in this example, a bed consists of uniform spherical particles of diameter 2.5 mm. So, particles are spherical in shape, it is having 2.5 mm diameter and density 5000 kg per meter cube. A liquid having viscosity 2 millinewton second per meter square and density 1050 kg per meter cube is used to fluidize these particles, we have to calculate minimum fluidizing velocity. So, how we will calculate minimum fluidizing velocity? If you remember second lecture of week 3, there we have discussed derivation of different expression which can be used to calculate minimum fluidizing velocity analytically. There we have discussed expression with this spherical particle. There we have discussed expression of minimum fluidizing velocity for spherical particle and for non-spherical particle as well. So, for spherical particle we have the expression for Reynolds number as well as Galileo number. Therefore, first of all we will proceed to calculate Galileo number, and that is Ga equal to d cube rho s minus rho g by mu square. Putting all values over here, diameter we know, density of fluid and particle we know, viscosity of fluid we know. So, considering all values, putting all values over here, we can calculate Galileo number as 1.59 into 10 power 5. So, Reynolds number relates Galileo number for spherical particle in this equation, where Reynolds number mf is the Reynolds number at minimum fluidizing condition. So, for EMF 0.4, because we do not know the voidage, so we have assumed voidage as 0.4. So, Reynolds number mf should be obtained by this expression while keeping all values, while keeping the value of Galileo number here. So, the value of Reynolds number mf should be 54.724. Once we know Reynolds number at minimum fluidizing condition, we can calculate minimum fluidizing velocity. So, that should be mu by d rho Reynolds number mf. Putting all parameter over here, we can obtain minimum fluidizing velocity as 0.0417 meter per second, and that is 41.7 mm per second. So, in this way we can calculate the minimum fluidizing velocity. Now, here I am having second example, and in this example liquid having density 850 kg per meter cube and viscosity 5 millinewton second per meter square is passed vertically upward through a bed of catalyst which contains approximately spherical particles of diameter 0.15 mm. So, you see diameter of particle is very small and density 3000 kg per meter cube. So, here again the bed of spherical particle with the very small diameter. So, bed is packed such as particles of diameter d are closely packed in cubes of side 2d. So, this is the important line, like here we have two particles in single side of cube. So, side of cube should be 2d. Compute the mass flow rate per unit area of bed at which fluidization and transport of particles occur. So, here we have to calculate mass flow rate per unit cross sectional area when fluidization will occur and when particle will be transported. So, when we are considering fluidization condition, what happens that when fluidization will occur when minimum fluidizing velocity condition will be achieved. So, first of all we have to calculate minimum fluidizing velocity, and then that should be multiplied with density so that we can calculate mass flow rate per unit cross sectional area. So, let us start the calculation. First of all we have to calculate minimum fluidizing velocity, and as here we are having a spherical particle size and diameter of particles are very less, that is 0.15 mm. So, as it is very fine particle, so Karman-Kozeny equation will be applicable over here. So, here we have we can assume laminar flow. So, so Karman-Kozeny equation will be UMF equal to 0.0055 EMF cube by 1 minus EMF d square rho s minus rho g by mu. So, here we should know value of EMF along with other parameters. So, other parameters are already known to you, EMF we should calculate. Once we know the minimum fluidizing velocity, we can calculate mass flow rate per unit area of the bed, because here we have multiplied with density. So, when we multiply density with the velocity, we can get mass flow rate per unit cross sectional area, but before that we should calculate voidage. So, how we can calculate voidage? In this problem, diameter of particle is d and two particles will lying on one side of the cube. So, what is the shape is basically cubic, we have to consider, of side 2d. Through this way we can calculate, through this way the packing is done. So, when we consider the cube, side is 2d. So, when, for example, if we are considering this phase of cube, okay, so here if this is one side, so two particles will here. Similarly, here we have two particle, here we have two particle, here we have two particles. So, if we are considering cube, this side of cube of side 2d, it means 4 particle will lie over here. Similarly, 4 particle will lie over here, because this side should also have length as 2d. So, 2 particle will lie over here. So, in this cube, when side 2d is considered, it means total 8 particle will be used to prepare this cube. So, volume of the spheres is equal to 8 pi by 6 d cube. So, 8 should be, because we have seen that 8 particle will lie in cube, and this is the volume of single sphere, that is pi by 6 d cube. So, in this way we can calculate total volume of sphere. Now, volume of enclosure is, because side is 2d, so 2d cube, that is 8d cube should be the total volume of enclosure. Now, how we can calculate voidage? Voidage can be defined as the total volume of liquid divided by the volume of enclosure. Volume of liquid means volume of enclosure minus volume occupied by the sphere. So, that should be 8d cube minus 8 pi by 6 d cube divided by 8 d cube. So, value comes as 0.476. We can take this 0.48. Once we know the value of voidage, we can calculate minimum fluidizing velocity by this expression. So, while putting all values in this expression, we can calculate minimum fluidizing velocity as 1.11 into 10 to the power minus 4, and mass flow rate, when this velocity will be multiplied with density of solid, we can calculate mass flow rate at which fluidization will occur, and that should be equal to 0.0944 kg per meter square second. So, this is the condition at which fluidization will occur. And let us start the second part, where we have to transport the particle. Now, how the particle will be transported, that we have already discussed, that when the velocity of fluid would be equal to or greater than the terminal falling velocity of the particle, then only it can be transported with fluid. So, here we have to calculate terminal falling velocity. Now, to calculate terminal falling velocity, first of all we should understand in which zone particle is moving. So, as we have discussed earlier, the diameter of particle is very small. So, we can assume the laminar flow over there, and once laminar flow will be there, we should apply Stokes law over here. So, in Stokes law, terminal settling velocity is equal to d square g rho s minus rho by 18 mu. Putting all values over here, we can calculate terminal settling velocity as 0.0052 meter per second. Now, once we know this, we can calculate Reynolds number, and that Reynolds number comes as 0.134. So, you should understand that as this Reynolds number is less than 0.2, the Stokes law can be applicable easily over here. So, once we have the terminal falling velocity or terminal settling velocity, we can calculate required mass flow rate while multiplying this with density of solid. So that comes as 4.42 kg per meter square second. So here you should understand how we have calculated mass flow rate for fluidization condition and for transportation condition. So here we are discussing third example for liquid fluidization, and in this example bed voidage E is related to fluid velocity UC for particulate fluidization of uniform particles as UC by U naught is equal to E raised power n. So here terminal settling velocity U naught is considered. For particles of glass with free falling velocity of 40 mm per second and 20 mm per second, the index n has a value of 2.6. So you see what is given, that here we have two particles, one is falling with 40 mm per second settling velocity and another one is falling with 40 mm per second velocity and another is falling with 20 mm per second velocity, n value is given as 2.6. If a mixture of equal volumes of two particles is fluidized, what is the relation between voidage and fluid velocity? So here you see what we have to calculate is the velocity as well as voidage relationship. Velocity means the UC as a function of E, that we have to find. So let us start the solution. Here we have considered unit volume of each particle as 1 meter cube, because if you consider the problem, it is given as the mixture of equal volumes of two particles has to fluidize. So in that case volume of two particles should be same, and that we have assumed as 1 meter cube. Now voidage of large particle is E1 and volume of liquid is E1 by 1 minus E. So how we define E1? E1 should be equal to volume of liquid divided by volume of liquid plus volume of solid. So when we solve this equation and calculate volume of liquid, it will come out as E1 by 1 minus E1 into volume of particle, and that we have taken as 1 meter cube. Similarly, voidage of a small particle, that is E2, volume of liquid is E2 by 1 minus E2. So volume of liquid we have defined. Now total volume of the solid, that is because equal volume, so 2 meter cube is there. Total volume of liquid we have derived in the last slide, and both expressions should be added. So total volume of the system is volume of solid, that is 2 plus volume of liquid. So this is total volume of system. Now voidage is volume of liquid divided by volume of the system. So putting all expressions over here and resolving it, we can have voidage as E1 plus E2 minus 2 E1 E2 by 2 minus E1 minus E2. This is the voidage. And in the problem, falling velocity of particle 1 is 40 and second is 20. So free falling velocity ratio is 2 is to 1. Then E1 can be defined as E1 equal to U by U naught 1 power 1 by 2.6. So this is the expression of E we have given, and for first particle terminal settling velocity is 0.01, and similarly for second particle E2 can be U by U naught 1 by 2 because it is half than the 1 power 1 by 2.6. So you see we can have E2 in terms of E1, and that should be E2 should be equal to E1 to 1 by 2.6, and E1 should be U by 40 1 by 2.6. Now substituting E1 and E2 in this equation, we can find this equation, and resolving it we can get equation of this form. Further resolving the expression of E as a function of U, we can get this expression, and then we can further simplifying this, and once we collect value of u, we can obtain equation as u power 0.7692 minus 3.649 1 plus e u power 0.3846 plus 13.8 e equal to 0. So, this equation we have obtained. Now, this is quadratic equation. How we can say? Because this power is just double than this. So, this is the quadratic equation. Once we solve this quadratic equation, we can get u power 0.3846 is equal to 1.824 1 plus e and this expression. So, here you see plus minus both components are available because this is quadratic equation. So, what is the correct expression of u and e? To know this, we have to draw the relation of u and e for plus component as well as for minus component. So, when we are drawing graph with positive component, then here we have u and voidage. So, this flat curve and then slight increment. So, here we have flat curve and then slight increment is observed. Further, if we draw the minus component, here we have u in mm per second and here we have voidage. So, here voidage and so here velocity is continuously increased with the voidage. So, when we consider first graph, here flat curve is obtained. However, we know that when the velocity increases, voidage increases. So, that should be in continuous relationship. So, here when we are comparing positive component and negative component gives more realistic relationship, and that should be the final relation we have asked to draw between u and e. And here we have summary of the lecture. In this lecture, liquid solid system, that is liquid fluidization, is discussed. Relationship between fluid velocity and voidage is described, and finally we have discussed few examples on liquid fluidization. And here we have the references through which you can read liquid fluidization in detail, and that's all for now. Thank you.